All right, so this number 9 on 5.2 wants to know is which of the following statements could be false based on this interval. And again, because they're equal signs here, this, oops, I got it right up here. This thing right here is the same as, including pi over 2 to 7 pi over 4. So we are talking about from these endpoints. So first of all, we want to know, is this thing continuous? Is this thing continuous from here to here? And the answer is going to be yes. All right. So if you wanted, you could look at this on a graph. If you want to graph it, you can. And you only want to go from pi halves to 7 pi over 4. So if I'm thinking about my unit circle, pi halves is right up here. This is where pi halves is. And my ordered pair there is 0, 1. And 7 pi over 4 is right down here, the 45-degree angle in the fourth quadrant, 315 degrees. And my ordered pair there is radical 2 over 2 to negative radical 2 over 2. Okay, so what I need to do is I want to find out, first of all, by extreme value theorem, are we guaranteed that there is some value less than g of x? Is there some value less than g of x? Okay, so on this interval. Well, does the extreme value theorem give us does it say anything about guaranteeing that there are values less than some other value? What does the extreme value theorem tell us? Anybody out there in this wonderful world can tell me that? Can somebody unmute themselves and tell me what it says?
That there is a value less than or equal to somewhere in the interval. If it's
okay, now we're talking extreme value theorem. What does the extreme value theorem tell me? It's on the front page of the notes. It's in a little box over to the right side. I think it's on the front page of 5.2.
If f is continuous on a closed interval a and b, then f has both a maximum and a minimum on the interval.
Okay, so what does that mean? What is that actually telling us?
The maximum and minimum is on the interval.
I couldn't hear that.
The maximum and minimum is on the interval.
Okay, that means that we are guaranteed on that interval that there is going to be a maximum value and a minimum value. That's what it says. It says we are guaranteed a maximum and a minimum value. So I guess my question to you is going to be, is EVT going to tell us that something is less than something else? It says that there is going to be some c that's less than or equal to everything in g of x. Is that telling me that there's some value here that I'm going to plug a c in that we're guaranteed that has to be less than or equal to everything here? Does this tell us that? Does extreme value tell us this?
No.
Okay, we said the extreme value guarantees that we have a minimum value and a maximum value. Now see, this thing right here is every y value. Every y value. This is saying, we are saying there's a specific point that has to be at least the bottom of every y value here. This has to be in other words, this has to be the lowest value on there. Does extreme value theorem guarantee us that we can find a lowest value, a value that's less than or at either less than or equal to every y on this interval? Does
Yes.
extreme value theorem tell us that?
Yes, it does.
It does. We are guaranteed there's a minimum, and that's saying this would represent the minimum because it's less than or equal to every point here. So it's the smallest. So this one's true. because this says we're guaranteed a minimum. Then this one says, hey, are we guaranteed that this thing is going to be, that there is some point that's greater than every one of these or equal to? And it's saying equal to because the lowest point will equal the lowest point in the graph. So is this one also guaranteed? Is that one true?
Yes.
Yes, because that is the maximum point right there. So this says we're guaranteed a minimum. This one says we're guaranteed a maximum, which is what the mean value theorem says, okay? Now the intermediate value theorem says that we have to have a value between these. So let's see what this says. There is a value of C such that, okay, so let's go down here and get this other one that doesn't work. This says by mean value theorem, is there a value of C such that there's a derivative that equals the slope of the endpoints? Okay.
Yes.
So what's got to be true to use the mean value theorem? G has to be what?
Continuous and differentiable.
Anybody tell me the things that got to be true to use mean value theorem?
Continuous and differentiable.
That's right. It has to be, the function G has to be continuous and differentiable on the interval. And the continuous part, we're supposed to say includes the intervals. Oops, that's a 4, isn't it? And differentiable does not include the endpoints because the endpoint, you cannot do a derivative at an endpoint. Okay, so first of all, is this function continuous? Is there anything that you can't put into x? I mean, from pi over 2 to 7 pi over 2? The answer is no. And is this thing a smooth curve? And the answer is yes. You can do the derivative of this because you put this to the half power and do chain rule. So these two things are okay. So we got to ask ourselves, are we guaranteed that there is some derivative that equals the slope of the endpoints? Well, that is the mean value theorem. So this one is also true because this is exactly the mean value theorem. Now the intermediate value theorem is what I just told you. It says you have a lowest point and a highest point, or maybe I shouldn't say lowest, but between pi halves, I guess we could actually do this. You got to plug 0 in here. So when you plug 0 in here, you get 1. So if I do G of pi halves, you put pi halves in here, the x value is 0, so you get square root of 1. That's 1. And then you do G of 7 pi over 4. And that's that radical 2 over 2. So this thing equals the square root of 1 plus radical 2 over 2. I mean, you could simplify all that stuff if you wanted. So what does the intermediate theorem tell me about the numbers between here and here? What does the intermediate value theorem tell me that I just went over? What did we just say the intermediate value theorem told us about all the values between the bottom and the top? What does this thing tell me?
That they all are there, like they're all
That
represented.
every y value between 4 and 36 must be on the graph. In other words, every y from here to here, every y value must be hit between 4 and 36. Every y value must be hit. That's what IVT tells us. So is this thing right here telling us that every value between these two y values is going to be hit? Is that what this means?
No, it's just saying that the
No,
average.
this is saying that G of C will equal the average y value. You see how you're adding the two y values and dividing by 2? This is saying there's a C value that will be the average of those two. Well, that's not what the intermediate value theorem tells us. The intermediate value theorem does not say that you are going to have an average value of the y's. Okay?
Wouldn't the average,
That is not the intermediate value theorem. The intermediate value theorem says every y value would be hit. So in order to make this true, instead of this, if they would have said this, that there's a g of c, or there is some value of c such that, instead of saying any of this, if they would have said g of, let's see, 1 plus this. So this is going to be bigger than that one, right? Because you're taking 1 and adding something to it to do a derivative, so this is bigger than that. So if they would have said this, that there is a c value, between 1 and the square root of 1 plus radical 2 over 2, if they would have said this, this is the intermediate value theorem. This is saying we are guaranteed that there is some y value between the two endpoints. You understand the difference?
I do, but the tricky part, I guess, is like, wouldn't the average of those two values be like between?
Well, okay, I understand what you're saying, that the average of two values is normally between them, right? But the intermediate value theorem does not say that the y will equal the average of those two values. So we have to use the average, we have to use the actual theorem. What it tells us is what we have to get out of it. Okay?
Okay.
All right. I hope that helps. Does anybody else have anything? I'm going to stop this recording for a second and see if we got any other questions that we can record. All right, so this is 5.3, number 3. And, wrong button. We want to know increasing or where the intervals are increasing, decreasing. And again, we want to use the sign chart in order to help us analyze where this function is increasing, decreasing. And I'm going to tell you this again, whenever you want to find a maximum or minimum, or whenever you want to find if a function is increasing or decreasing, we always want to use the first derivative. So if it ever asks those questions, you're going to want to find, or critical numbers. Critical numbers are first derivative also. So we want to find the critical numbers first. So I need to do the derivative of this. And can someone tell me, is that, let me see if I can see it on the paper. Is that 2/3? Is that power 2/3?
Yes.
Okay, so I got to do chain rules. I take my 2/3 to the front, leave the inside the same, lower the power by 1. And then take that times the derivative of the inside part. Well, the derivative of x is 1, so that's not going to change anything. And then I would want to simplify this if it were me. And some people might want to write it in a radical form. You don't have to, but if you wrote it in a radical form, that would be the cube root of x plus 1. So this is the problem that I'm dealing with right here. Okay, so I need to find the critical number. So critical numbers occur where the derivative is 0, and I want you to write this down every time to make sure you check them all out. So I'm going to take 2/3 times the cube root of x plus 1. Now, if you watch the video, I said whenever you do this, you never have to write the denominator part down, because the first thing you do is multiply that over, which is where I would have started and it's gotten 2 equals 0, because I would not have written this denominator down. Because whenever you're setting something equal to 0, you take the denominator over, so it will always go away. So where does 2 equal 0? Anybody? Where's 2 equal 0?
Nowhere.
Nowhere. So this is not true. If you think it is true, you give me $2, I'll give you nothing, and we'll call it even. So I get no critical numbers from this. There are none from that. The other thing that can happen is wherever the derivative is undefined can be a critical number. Well, undefined critical numbers occur where the denominator equals 0. So I'm going to divide each side by 3. You know what? I think I did this problem on video already. I think somebody asked this yesterday. So I divide each side by 3, then I'm going to cube each side, and then I'm going to subtract 1. So there, this is my critical number right there. That's my critical number. My critical value or critical number is x equals -1. So the chart I make is I make a number line and I put -1 on there. Now, do you notice there's no intervals here? Over here, there are intervals. You see the intervals here? So that means on this, if this were the one I'm doing, you would have 0 here, and you would come out here, and you would put a maybe parenthesis to tell you that that doesn't work, but you'd put 2 pi there. And is this a parenthesis too? It is. So we would have it like this. These two points don't work, but everything between there does. But there's no interval on this one, so it goes left forever and right forever. So this is the z, this is the critical value. So what I want to know is over here, what kind of values do I get out for this derivative thing right here, for this thing? Well, I hope you can all see that no matter what I put in for x, the top is positive because it's a 2 forever. And then I'm going to put a -2 down here. Well, -2 plus 1 is -1. The cube root of a negative is negative. Whenever you have an odd root of a negative, it's negative. You can't do the even root of a negative. They don't exist. So this is negative times a positive, so this is negative. So over here, our function is decreasing. And then I come over to this side, and I plug a number in. I'm going to plug 0 in because it's greater than 1. 0 gives me the cube root of 1, which is positive. And a positive times a positive is positive. So over here, we have positive values. So what I know is that the function f, the original function f of x, is decreasing from, and then we would say -infinity to -1. Now, you can put a bracket there. I almost recommend you always put parentheses because for some reason they don't count that wrong. But this graph is decreasing all the way to there. And then the reason is because, and I want you writing this because this is the justification. You doing this is just for you. This tells the grader nothing. And by the way, something else I would do over here is I would label this number line f prime for me to know that's f prime. Because later on, we're going to do stuff with second derivative. So put an f prime by this number line, meaning what that tells me is I'm plugging these numbers on each side into f prime. Okay, and the reason is because f prime is less than or equal to 0. You can put equal to there and it's okay. F prime is less than 0 on the interval -infinity to -1. Okay? So this is negative. Then I would say f of x is increasing from, and then that would be -1 to infinity because f prime is greater than 0 on the interval -1, that's parenthesis, -1 to infinity. So that's what you would write on that. So that stuff after the because, that's called the justification. So I would like you to try to practice using the justification because that's going to be on the AP test. Does anybody else have anything they need me to do?